All doing good. So in this video lecture, we'll be learning something more about solitons. So a nonlinear Schrodinger equation. So we have already discussed any system can be modeled in the form of an equation. So in order to model the nonlinear behavior of a signal propagating through an optical fiber, we are using the nonlinear Schrodinger equation. And solving this nonlinear Schrodinger equation, we get solitary solutions. And these solitary solutions are known as solitons, which is a special wave. Okay, so the basic form of this equation is minus j dou u by dou z equal to half dou square u by dou t square plus n square u square into u minus j alpha by 2 into u, and the function u of zt is a pulse envelope function, and z is the propagating distance along the fiber, n is the order of the soliton, alpha is the coefficient of energy gain per unit length with negative values of representing energy loss. And as you can see from the equation, it is divided into three parts. The first part is the group velocity dispersion parameter. The second part is the cell phase modulation or the refractive index dependence on the light intensity, that is the nonlinear effect, and the last term is energy loss or gain. So on solving this nonlinear Schrodinger equation, we get the solitary solution. So we can see the solitary solution, that is UZT equal to secant t expression Jz by 2. So the secant t is a hyperbolic pulse waveform that we obtain in the form of solitons. Now this is the block diagram for a optical fiber soliton transmission. So you can see as like the any communication system, this communication system also had three parts: the transmitter part, the channel part, and the receiver. So in the transmitter part, the data signal in the non-return to zero format is given to the multiplexer. So the multiplexer multiplexes the signal to a Mach-Zehnder interferometer modulator. So the Mach-Zehnder interferometer modulator works on the principle of interference, and the carrier signal is given by the DFB laser. So the modulated signal and is then converted into return to zero format with the help of the clock signal, and this signal is then given to the channel. The channel has optical amplifiers. The optical amplifiers for compensating the regenerative losses, and the dispersion compensation unit is to compensate for the dispersion. We'll be learning about why using the dispersion compensation unit. This is to avoid the GH effect, and from there to the receiver will be exact copy of the opposite of the transmitter. We'll be converting the signal back to non-return to zero format with the help of the clock signal. The clock signal at the transmitter side and the receiver side are synchronized, and then it is demultiplexed, and then we get the signal out. So this is how an optical fiber soliton transmission takes place. So the next topic is GH effect. GH effect is also known as Gordon-Haus jitter. It was first studied in 1986. So what is this GH effect, and from where is this GH effect happening? So in soliton transmission system, we have a laser which is for the continuous wave generation. So associated with the laser, we know there is amplified spontaneous emission noise. The basic principle the principle of working of a laser is stimulated emission, but we also know as there is some spontaneous emission that happens in a laser when some electrons in the upper state when it is done with it, like when the time there is a fixed time where which each of the particles can stay at a particular level. When that is over, that has to come back to its lower level, releasing some amount of energy, which results in spontaneous emission noise. So because of the spontaneous emission noise from the laser in a soliton transmission system, there is a change in phase and the frequency of the signal or the soliton that is transmitting through the transmission system, which causes a random shift in the soliton. Okay, so because of this GH effect, that is because of the amplified spontaneous emission noise, there is a random phase shift or the frequency shift that is happening in the soliton, which is known as the Gordon-Haus effect or the GH effect. And this Gordon-Haus effect can be overcome by using certain filters. linear filters or by using dispersion compensation units. So in our soliton transmission system, in the channel after the optical amplifiers, we have seen the dispersion compensation unit. So this dispersion compensation units is to overcome the GH effect in the soliton optical transmission system.